Welcome to lecture 2, week 1. In this week, we are talking about introduction to optimization. In lecture 1, we have talked about very briefly about optimization, and we have talked that optimization is a mathematical technique to find out the best possible solution to your problem. So, if optimization is a mathematical technique, it is quite natural that the optimization problem will be stated in terms of some standard mathematical form. So, in this lecture, we will see what are the components of an optimization problem, so that in later class we can formulate the optimization problem. So, after talking about the various components of an optimization problem, we will also briefly talk about the various classification of optimization problem that exists. So, today's topic will be statement of an optimization problem and classification of optimization problems. All optimization problems are stated in some standard mathematical form. You have to identify the essential elements of a given problem and translate them into a prescribed mathematical form. The following are the requirements for the application of optimization problems: the design variables or decision variables, the objective function, the constants, the process model. So, you can perform a mathematical optimization if we are sure, or if you know how to formulate the objective function, what are the decision variables, how to formulate the constants, and maybe we may also require a process model that describes the behavior of the system under optimization. So, now we will talk about the decision variables or design variables, the objective function, the constants, etc., in some more detail. The first task of optimization process is to identify the underlying design variables that influence the system being optimized. So, you need to know what are the variables that influence the system we are optimizing, and you are trying to find out the optimal values for these variables. It may happen that some variables will influence the system's output or the system's response or the system's behavior to a large extent, and there will be some variables which may be bit insensitive, meaning that those variables do not influence the behavior of the system much. So, the variables which heavily influence the system will be considered as decision variables or design variables, and the variables which do not influence the system's response that you are interested in may be considered at some constant level. That means, we can assign some constant nominal values to those variables. So, these design variables or decision variables are varied during optimization process in order to find an optimal values of these variables, so that we can achieve the optimization goal. The optimization goals are usually maximization of some profit or minimization of some cost. This is in terms of economic consideration. Later on we will see that we can also consider technical aspects and relate maximization and minimization problems. So, some examples of design variables or decision variables may be: you find the optimal reactor temperature, optimal feed rate, maybe a constant feed rate, or maybe a feed rate profile. That means, the function of the feed rate with respect to time. So, feed rate may or may not remain constant with time. Number of plates in a distillation column, reflux ratio, optimal batch time, to maximize say product concentration, reactor yield, etc. A practical problem may involve many design variables. Some of these may be highly sensitive and heavily influence the process being optimized. We choose them as design variables, and others which are not so sensitive variables may be kept constant at some nominal values. If all the design variables are fixed, then there is no scope for optimization. Thus, one or more variables must be relaxed so that the system becomes an underdetermined system, which has, at least in principle, infinite number of solutions. So, if all the design variables of a given optimization problems are fixed, then there is no scope for optimization, because your system is completely defined and there will exist an unique solution to the problem. So, for optimization to be possible, we must have an underdetermined system, so that in principle there will exist an infinite number of solutions and the optimization technique will find out the best possible solution among several alternatives. Next, let us come to objective function. A suitable objective function, also often known as cost function, is defined in terms of design variables or decision variables and other problem or process parameters. So, the objective function or the cost function is a suitable function of design variables and other problem or process related parameters. The objective function may be technical or economic in nature, which needs to be either maximized or minimized. Examples of economic objectives: you want to maximize the profits for an operation, you want to minimize the cost of production. So, you must formulate a function that tells you how much profit you will get, and this profit expression will be a function of decision variables. So, we will find out the optimal values of those decision variables that will maximize the profit. Similarly, the objective function may also be minimization of cost of production. So, here also the cost of production will be a mathematical expression which is a function of decision variables. Examples of technical objectives: maximize reactor yield, minimize size of an equipment, minimize error during curve fitting, minimize environmental impact, etc. Remember, in all the cases, the objective function will be a function of decision variables. So, you are going to find out the optimal values of the decision variables that maximize or minimize the objective function. It can also be said that the technical objectives in an industrial operation will ultimately get reflected in economic objective function. Let us consider a simple example, and this will tell you that we may have single objective function, we may also have multiple objective function. Although in this course we will essentially talk about optimization problems with single objective function. So, let us consider a simple example of travel plan for a long trip. So, you are going for a long trip, that is a very long trip. Let us say you can take train or you can travel by air, and you have different options. There are flights which take less time than the others, but obviously the ticket price will be different. Similarly, there are say super fast trains which will take less time, and let us say there are regular trains which will take more time, but again then the ticket price will be different. So, if we want to optimize my travel plan, I may look for two things. You can minimize the price of the ticket, you can minimize the travel time. If there is no restriction on travel time, obviously I will try to minimize the cost of the ticket. If money is no consideration, I will try to minimize the travel time. So, a single objective optimization problem may be either minimize the ticket price, that is F1, or minimize the travel time, that is F2. But we perhaps will try to minimize both. We will try to minimize travel time as well as we will try to minimize ticket price. But is this possible? So, if you plot cost, that means ticket price versus travel time, you see you get a plot like this, which says that if cost is higher, the travel time is less. If cost is more, the travel time, if cost is less, the travel time is more. So, basically these two objectives conflict with each other. There are several real life problems where you have more than one objective functions, and these objective functions conflict with each other. Such optimization problems are known as multi-objective optimization problems. Although we will talk about only single objective optimization problems in this course, there are several important real life multi-objective optimization problems, and specialized optimization tools are available for solutions of multi-objective optimization problems, such as genetic algorithms. One way to solve a multi-objective optimization problem is to convert it to a single objective optimization problem. I can do that by taking weighted average of the individual objective functions and can formulate a composite single objective function, and then can apply the single objective optimization techniques. This is known as weighting method. So, what I have done is I am taken a new objective function f, which is W1 into F1 plus W2 into F2. So, W1 W2 are different weights and W1 plus W2 equal to 1. So, once I formulate this problem, I can apply the techniques that we learn in this course for solution of optimization problem with single objective function. But please note that specialized techniques are available, and for better solution we should apply those specialized algorithms for solution of multi-objective optimization problems. Next, talk about the constants. The constants represent some additional functional relationships among the decision variables and process parameters. The constants originate as decision variables must satisfy certain physical phenomenon and certain resource limitations. Let us now see what are the various types of constants that we will encounter with. So, once again the constants represent some additional functional relationship among the decision variables and the process parameters. So, this is not an objective function, this is a constant function which is again a function of decision variables or other process related parameters. The constants will appear because the decision variables must satisfy certain physical phenomenon or certain restrictions or certain resource limitations. Variable bounds. The variable bounds is represented as, if x is decision variable, let us say x varies from 0 to 1 or x varies from 2 to 5. Let us say the diameter of a can that I am going to design will be lying in between 3 centimeter to 10 centimeter. So, we will write x is greater or equal to 3, less or equal to 10. Equality constants. So, here the constant function will have equality sign, it will be an equation. Equality constants that frequently appear in chemical engineering optimization problems are, say, sum of mole fractions should be unity, component balance equation in distillation column, component balance equation in blending process, all this will lead to equation. So, that is equality constant. Inequality constant will be of less or equal to type or greater or equal to type. Note that less or equal to type can be converted to greater or equal to type and vice versa by taking the minus sign. Examples of inequality constants: in packed bed reactor, temperature should be less than the catalyst deactivation temperature. So, you can write temperature T must be less or equal to the temperature at which the catalyst becomes deactivated. Stress developed anywhere in a component should be less than maximum allowable stress. We will represent acidic condition as pH less than 7. So, these are all examples of inequality constant. The process model. A process model is required that describes the manner in which the decision variables are related. The process model also tells us how the objective function is influenced by the decision variables. A model is a mathematical equation or is a collection of several equations that define how the decision variables are related and the acceptable values these variables can take. Optimization studies are carried out using a simplified but reasonably accurate model of a real system. Working with real system is time consuming, expensive as well as risky. So, a realistic process model which represents the behavior of the system under optimization quite well is necessary for mathematical optimization to perform. Now, so we have seen that the components of an optimization problem are decision variables, objective function, constants. So, given a set of design vector, given an objective function, given set of inequality constraint, given a set of equality constant, the general problem statement will be: you minimize function f x by finding out the decision variable x, and the decision variable x must satisfy the constants: inequality constant g x greater or equal to 0, equality constant h x equal to 0, and the bounds on decision variable x, which is bounded between lower bound and upper bound. In terms of words, we can say the find the values of decision variable x that minimize or maximize the objective function while satisfying the constants. And this is the mathematical representation of a general optimization problem. So, you have the design vectors or decision variable vectors x, which may have n components x 1, x 2 up to x n. That means, there are n decision variables to be found out optimally. You have an objective function f x. So, the objective function is a function of the decision variable x. You have set of inequality constant g x greater or equal to 0. You have set of equality constant h x equal to 0. Then the optimization problem statement is minimization f x subject to g x greater or equal to 0, h x equal to 0, and x is bounded between lower bound and upper bound. Note that the minimization of function f x and the maximization of minus f x is equivalent. So, a general problem statement may be in terms of minimization of f x, it may also be maximization of f x, because minimization of f x and maximization of minus f x are equivalent. It can be clearly seen from here. So, here I have plot a function, single variable function f x. You can see that at x star there is a minimum. If you now plot the function minus f x, it will be the mirror image and the maxima will appear at the same value of x star. So, minimum of f x is same as maximum of minus f x. Next, let us talk about constant surface. The set of values of x, that means decision variables, that satisfy the equation g x equal to 0 forms a hypersurface in the design space and is called a constant surface. So, you have g x greater or equal to 0 as constants. So, now let us say I have in this example I have 4 constants g 1, g 2, g 3, g 4. So, you plot this g x equal to 0 and the region that is bounded by g 1, g 2, g 3, g 4, these 4 constants, that means this green color region is known as feasible region. So, your optimal solution must lie within this region, because the optimal solution has to satisfy these constants. So, we have to find out the optimal solution within this feasible region. If I also have equality constant, like say here I have an inequality constant g x greater or equal to 0, I have another inequality constant g x greater or equal to 0, axis supposes as linear inequality constant. So, x greater equal to 0, y greater or equal to 0, those axes are considered as linear inequality constant. And if I have an equality constant which is shown here, the decision variables, the optimal decision variables or the optimal solution will lie in the feasible region. If there was no equality constant, but there was only say another inequality constant like this is your feasible region. But in the presence of equality constant, the feasible region is along this heavy line which represents the equality constant. So, we must find the optimal solution along this line which is within the feasible region, But since the optimal solution has to satisfy both equality and inequality constant, it has to lie on the heavy line which represents the equality constant. Objective function surface. The locus of all points satisfying f x equal to c, where c is a constant, forms a hypersurface in the design space and is called objective function surface. So, my objective function is f x. So, I assign different constant values to the objective function, f x equal to c 1, f x equal to c 2, f x equal to c 3, so on and so forth. And so, if I do that, this will form a hypersurface in the design space, and this will be known as objective function surface. So, different values of the constant c will form a family of hypersurfaces, which are known as objective function surface. Look at the figure. So, these are objective function contours corresponding to f x equal to c 1, f x equal to c 2, so on and so forth. As we go in this direction, the value of the objective function increases. That means, the innermost contour represents the minimum function value, next is c 2, next is c 3, and maximum is c 4. I want to minimize this problem, and let us say this is my feasible region, this hatched part is my feasible region. So, the optimal solution lie within the feasible region, and say this is the point which will lie in the feasible region and has the minimum value of the function, objective function. See, there exists this point, there exists this point which has even less value compared to this point, but they are outside the feasible region. So, the optimum point is this. Next, let us briefly talk about various classification of optimization methods or optimization problems. Optimization problems can be classified in various ways. One classification may be based on presence or absence of constants. Constant optimization problems are those which has one or more constants. Unconstant optimization problems are those which do not have any constants. The classification of optimization problem may also be based on nature of the equations involved. In case of linear programming problem, the objective function is a linear equation, all the constants are linear equation. In case of nonlinear programming problem, objective function may be nonlinear, the equations may also be nonlinear. In case of quadratic programming problem, the objective function is quadratic and the constants are all linear. The classification of optimization problem may also be based on the nature of the decision variables. In case of continuous optimization problems, the decision variables can take on continuous real values. In case of integer programming problem, the decision variables will take on only integer values. In case of mixed integer linear programming problem, you have a linear programming problem where the decision variables can take only integer values as well as real values. So, mixed integer linear programming problem. You can also have mixed integer nonlinear programming problem. Here your problem is nonlinear programming problem and the decision variables can take both real values as well as integer values. So, some decision variables will be taking integer values, some decision variables will be taking real values. So, they are MINLP. MILP and MINLP are also very important class of optimization problems in chemical engineering. We can also have classification based on local search methods or global search method. So, this will lead to local optimum or global optimum. Classification may be based on the number of objective functions. We can have single objective optimization problems, we may have multi objective optimization problems. Still another classification is possible based on whether the problem is deterministic in nature or there is an element of randomness which is known as stochastic optimization problems. So, there are various classifications and there is no unique way of classifying them. So, based on various criteria, we may have various ways of classifying the optimization problems. With this, we will stop here.